Okay, this is to cover Chapter 3 and a review session going over the problems that were assigned from the textbook. And so we're covering sections 3.1 to 3.6, and you were given this review sheet of topics that could show up on the test. So I'm going to walk through question by question and try to help you look for solutions here. The first one talks about looking for absolute extreme values. So we want to find the absolute maximum, and that will be, I'll probably write that as an ordered pair, and the absolute minimum. And we'll get an ordered pair for that. Well, if you recall, there are two categories from which the absolute max can occur. One of them is we can have absolute values or extreme points coming from the endpoints. So what I need to do on this is evaluate my endpoint 0, find out what its y value is by plugging it into g, and also let's evaluate g at 2 pi, the right endpoint. So that is going to be simply plugging it in and getting a value. The other possibility where we can find absolute min and max occur at it occurs at our relative mins and relative maxes, or on the critical points. And remember, critical points are coming from where the first derivative is equal to 0 or d and e. Well, that means I need to take a first derivative to get that information. So g prime of x is equal to 2 minus 5 sine of x. And then I want to find where it's equal to 0. So I'm going to set 0 equal to this. And let's add the 5 sine x over and divide by 5. So we get sine x equals 2/5. To actually get the value of x, we need to do a sine inverse to each side. This is the undoing function for us. So I get sine inverse of sine canceling there, and it'll bring out x is equal to the sine inverse of 2/5. Now it is time to grab your calculator and do sine inverse of 2/5. You'll find out that this comes in around 0.41. 0.4115, I guess. That is its x value. Now, because of the way trig functions work, just think of our unit circle. There are two locations where this could occur, and having an x value of so it's an angle measure where x is 0.41. Well, that also gives me a positive sine value when I'm over here coming up by 0.41. But what I need to do is I need to evaluate this coming from the counterclockwise position. So we know this is pi, so I'm going to take pi and subtract 0.41 from it, getting me a value of 2.73. So I actually pick up another x value here because of the way the unit circle works. We know there are two locations where the sine value is positive. In other words, there are two locations where sine of x will equal a positive 2/5. All right, so we've got those. Those are our critical values. A lot of work just to get those. I promise I won't give you a trig function on the test, but the application is still the same. Once we get our critical numbers, we're going to do the same thing with it. Critical numbers come off that first derivative. So here are my two critical values that I'm going to plug back into my original g function. So I'm going to have g of 0.4115, and I'm going to have g of 2.73. And need to get those values as well. So go to your calculator. You can go 0 plus 5 cosine of 0. Cosine of 0 turns out to be 1, and this will be a value of 5. 2 pi, I'll have 4 pi, because 2 times 2 pi will give me 4 pi, plus I'm going back to the original function, remember, 5 cosine of 2 pi. Well, that's going to be 4 pi plus 5, and roughly in my head I'm estimating this is 12.8 point something. It's a little larger than 12. You could get, if you have your calculator, you can get that value. For my other value, when I do G of 0.41, I'm getting out 5.41, and of 2.733, I get 0.88. Now, it is really just a complete comparison of y values. So I'm looking at these 4 y values. And the question is, which one's the largest? Well, it was the 12, and that occurred at 2 pi. So it'd be 2 pi, comma, 4 pi plus 5 as an ordered pair. The absolute min appears to be at 2.73, which gave me a y value of 0.88. There is problem 1. A little bit harder than necessary, maybe, just because of the complexities of the trig function. Number 6 is talking about Rolle's theorem and things that you should remember about Rolle's theorem. One is the hypotheses of Rolle's theorem. There are 3 things that must occur to Rolle's theorem in order to go forward and calculate using Rolle's theorem. So the hypothesis was 1, is f of x continuous on the closed interval? Continuous on the closed interval, and for us it's going to be on this closed interval from 0 to 4. Another thing we've got to talk about is f of x differentiable. This is differentiability on an open interval 0 to 4, so not including the endpoints. And the third thing is to check out these y values. So when I plug in x, do I get out the same y value? If all of this follows through and is fine, then we come up with a conclusion. And the conclusion of Rolle's theorem is, what is it? It's f prime of c equals 0, where that slope is 0. Now, looking over here, I know what this function is. It's an absolute value function. It has some transformations going on. It is shifted right by 2, and it is shifted down by 2. So just a quick little sketch would give me a function that opens upwards that would look something like this, shifted right and left. And now, if we're on the interval from 0 to 4, well, that places us from 0 out to 4, you know, maybe somewhere in this blue region. Let's call 4 out here. Probably be at that zeroing point. Is it continuous? Absolutely. I'm looking here, nice solid, never stops. But however, when I look, so this one's fine, but differentiability, it has that sharp point to it. It is not differentiable. So Rolle's theorem cannot be applied. Does not apply. And it is because the function is not differentiable on the closed interval from 0 to 4. Number 8, can the mean value theorem be applied? Okay, in order to answer this question, I first need to know some things about the mean value theorem and things I know about mean value theorem. Just like Rolle's theorem, it has 2 hypotheses that must be met. And it is f of x a continuous function on the closed interval, in this case, -2 to 1. The other thing is f of x differentiable on the open interval, -2 to 1. And then our conclusion, if those things follow suit, the conclusion is f prime of c is equal to f of b minus f of a over b minus a, where we interpret this as the slope of the secant line, or basically the line that passes through the endpoints 1 and the other x endpoint -2. And then this, of course, is our first derivative. Okay. Let's go check to see if this function is continuous. So here's our function, f of x is equal to 1 over x squared. Immediately when I read this question or saw this function, my eyes were really spotting the fact that I had a variable in the denominator. And when that occurs, I'm kind of on an alert. Are there some values that I cannot use? Well, indeed there are. Actually, there's just one. X can't be 0, can it? Because if x were 0, we'd be dividing by 0. So now the question is, what about the interval that we're looking at? Well, we're looking at from -2 to 1. 0 does fall in between -2 and 1. It is not continuous on that interval. So on this one, mean value theorem does not apply again. And that is because it's not continuous on that closed interval -2 to 1. So be ready to substantiate why it doesn't apply. Don't just say it doesn't apply. There has to be an obvious reason why it doesn't apply. One of those two would be it. Is it continuous? Is it differentiable? Okay, number 8. Find the points guaranteed by the mean value theorem for the closed interval. And we get a function with a rational exponent that is less than 1. That also grabs my eyes, and I'm thinking, oh my, that is going to put us on a cusp alert. And I think this function, without any shifting left and right, when it hits 0, we get out 0, but it does so in a cusp type fashion. And that would not be differentiable then at that sharp point at 0, 0. However, look at our interval. Our interval's fine, isn't it? It does not include that. So if I just highlight some regions where I see 1 to 8, you know, we're looking in this vicinity where x equals 1 out to x equals 8. And heck, that is continuous. And it's differentiable. How do I know if something's differentiable? Well, I'm looking for a smooth curve without sharp points or asymptotes, things like that. So this appears to be fine. So we should be able to conclude then that f prime of c will equal f of b minus f of a over b minus a. To do this problem, then I need to take the derivative, and the derivative will be 2/3 x to the 2/3 minus 1, or 3 over 3. That will be equal to f of b. F of b is an 8. F of a takes on the value of 1, and then 8 minus 1. So do some calculations. I'm going to clean up my left side. That will be a -1/3, so that'll drop that to the bottom as a +1/3. On the right, f of 8 is equal to, let's see, we've got 8 raised to the 2/3 power. Use your calculator if you want, otherwise I'm going to interpret this as the cube root of 8, and then I'm going to square it, minus the cube root of 1 squared over 8 minus 1, which is 7. All right, do a little calculating. I hope you realize that 8 is a perfect cube, and with that we can take the perfect cube of 8, get 2 squared becomes 4, minus the cube root of 1 is 1, and squared is still 1. So I'm going to pick up, 7 over 3 as the slope between the endpoints of my function on this closed interval. All right, that brings us to a problem that looks like this. I think the quickest way might be to cross product this and come out with a solution. So I'm going to get 14 equals 9 x to the 1/3. Let's divide by 9. It gives me x to the 1/3 equals 14/9. And I need to undo the cubing, or the cube root, so let's take and raise it to the 3rd power, cubing each side. That's going to give us an x value, and on the right, get your calculator. I don't know 14 cubed. I think 9 cubed is 729. There's our answer. One more problem on this video and then I'll start up another one. Number 16, it says find the critical numbers, if any, in the open intervals in which the function is increasing and decreasing. The easiest way for me to figure out if a function is increasing or decreasing, in my mind, is to use a sign chart. And in order to build a sign chart, I'm going to use the first derivative to get my sign chart. So let's go in and do a first derivative. G prime, I guess we're on G prime here. G prime is equal to, chain rule, 3 comes down, I get x plus 1 quantity squared. Derivative of the inside is simply 1. Now, in order to get my critical numbers, remember critical numbers come from f prime of x equaling 0 or f prime of x dne. So for that, let's take our derivative, set it equal to 0. In this case, the dne, I'm looking, there is a denominator without any variables. I don't have to worry. dne does not apply to this particular problem. In order to get this to be 0, I can focus on the inside of this. So, whoops, get that highlighting. If that equals 0, so does everything else. So x plus 1 equals 0. That means x is equal to -1. I have a critical point at -1. Hey, that's kind of nice because now we have a short sign chart. And get your value of -1 on your sign chart. And this is a first derivative sign chart. It'll give us information about f. And we just need to pick out a couple little test values, right? Something to the left, maybe I'll use -3. Something to the right, I'm going to use 0. And we will plug it back into the first derivative because we want to know what the first derivative sign is. Is it positive or is it negative? So -3 goes in. G prime of -3 would give us 3 times -3 plus 1 quantity squared. We'll square anything and you're getting a positive and then take it times a positive like a 3 and you're going to stay positive. The same can be said about 0. 3 times 0 plus 1 quantity squared. Anything squared is going to be positive, and 3 times positive is positive. All right, so we ended up with an increasing function. It increases and then increases more. Pretty typical of what you expect a cubic function to do, I'd say. So what are the intervals of increasing? -1, while this was our critical point, it was where f prime was equal to 0, remember, is a valid member of our domain. For our domain, x can be any real number. So I'm going to make my interval then go from -infinity to +infinity. That is where we have an increasing function. Temporarily, at that minute point of -1, it flattens, but then the very next point is going to be higher than that previous point. Let's call this one good. I will start up another video after this.